Hello, this is Mr. Gilmore with the 9.1, The Anatomy of a Circle. We begin our study of circles this chapter, and of course, with everything we've done in our system, we start with definitions. So let's start with what is a circle? A circle is a set of points in a plane, a given distance from a given point. Now, that given point that we are setting our set of points of given distance away from, we call the center. And that's actually what we use to name the circle. We use the name, since the center is a point, we label it with a capital letter, and then that is what we use to name the circle. So down below, we have what we call circle A, right? Because the center point has been named with the capital letter A. So just using the center name, we can call the circle called circle A. Now, point B, we're going to use this preposition here of being on the circle, which means point B is a part of the set of points that actually are made up of these points that are given distance away from this given point. Now, there's that given distance, right, from the center of a circle to the points on the circle, which we're going to give that given distance a name. It's called a radius. A radius is actually that segment that begins at the center of the circle and ends on the circle, which means the two endpoints of that radius are the center point and a point on the circle. So by definition, every radius of a circle equals every other. Is essentially what we're saying is because it's that given fixed distance, that means every radius is going to be the same length. A chord is a segment whose endpoints lie on the circle. So now if we were to choose 2 points such that their endpoints are on the circle, we call that a chord. Now there's a special type of chord though. We have what's called a diameter. A diameter is a chord that passes through the center of the circle. If we take a look down at our diagram below, we actually have a circle A with several points labeled on the circle. And what we're going to find are several different, what we call the radius, and we'll find chords, and we'll find the diameter. If we take a look, there are several radii. Radii is the plural for radius. For example, we have the segment AG, which is centered at A to a point on the circle G. We have AJ and AK. Both are also radii of the circle. Now for chords, remember the endpoints of a chord are simply a segment which the endpoints are on the circle. So HI is considered a chord, right? HI is a chord. And also JK is considered a chord. However, JK is a special kind of chord. As we see in our next part here with the diameter, JK is a diameter of the circle as well. But by definition, a diameter is a chord. We actually proved way back in our chapter 5 with our triangle inequality theorem that the diameter is actually the longest chord in any given circle, that we can actually prove that JK is longer than HI, something that we saw back with our triangle inequality chapter. Now, there's going to be an obvious relation that we now form between the radius of a circle and a diameter of a circle. So, by definition, the diameter passes through the center of a circle. Thus, each of the two subsegments that the diameter is cut into is really a radius by definition. Hence, the length of the diameter, which we'll label as the variable d, is twice the length of any radius r with respect to that given circle. So now we have this relationship of any given circle that the diameter is equal to two times the radius. That's going to be the relation that we're actually going to see come up later in today's lesson. Now, one more thing we're going to talk about the circle as far as its anatomy is known as the circumference. So imagine that we pick a point on our circle, any point that's on the circle, and we then begin to follow the circle around itself until we reach that same point that we started with. That total distance traveled is what we call the circle's circumference. Think about how we use the definition of the perimeter in a polygon as the distance total around any given polygon. The circumference is the total traveled distance around any given circle. So from point A all the way back around the circle to back to point A again, that's what we then have followed what's called the circumference of a circle, which the circumference of a circle is a distance, it's a length, which means we will find that it has measure to it. We'll talk about that measure later on today. Now, an arc, okay, as we dissect the circumference of a circle, we run into what's called an arc. An arc is a portion of a circle that connects points on that circle, meaning pick any 2 points on the circle and you can travel from that one point picked to the other point picked. However, you actually have a couple different directions you could have gone. You could have gone in a counterclockwise direction, or you could have gone in a clockwise direction, which is why when we then separate our arcs into 3 categories. Our first category is known as a minor arc. Minor arcs are less than half a circle. So by by what we're given in our first diagram, we actually have what's called a minor arc there. It is then less than half a circle with these 2 points chosen on our circle. There is this connection between the two, which is then the arc. However, with the arc being less than half, we call that a minor arc. The second diagram is actually one of a major arc. Major arcs are then more than half a circle. And that's just if we were to travel the other direction around the circle from one point to the other, we would then form a major arc. Last, we have what are known as semicircles. Semicircles are arcs that are precisely half of a circle. So any circle actually gets cut into two semicircles. And one relation we find with the semicircle is that this segment connected from the one point on the circle to the other is actually a diameter. So yes, diameters cut semicircles, and then conversely, we could say that if we're given a semicircle, it is cut then by a diameter. Now, how do we name arcs? It's very simple. Okay, a minor arc gets 2 letters to name it. Because the arc is less than half of the circle, it's very simple just to use 2 letters, which then gives the direction in which that arc is going. So down below in our diagram, we have the arc AB. That's a minor arc. If I only use 2 letters, it means I'm going in the direction from the shortest path I could take from those 2 points chosen. A major arc, though, we have to get a little creative because we want to make sure the reader knows which direction we're going. And with a major arc, we're going to go the longer direction around a circle, which means a major arc needs 3 letters. So down below in our diagram again, we have the major arc of ADB. So notice that with the third letter in there, in the middle between our A and B, it's going to give us a direction, not just for us, but for the reader as well. So this is saying go from point A, cross down to point B, and then around the circle over to point B. That's going to be our major arc. We have to use 3 letters. Semicircles also are named with 3 letters as well. So down below, we actually have 2 semicircles, ABC and ADC. Because I couldn't just say, take a look at semicircle AC, you wouldn't know which half of the circle actually I'm referring to, which means that's important that the semicircle also gets 3 letters. ABC and ADC would be then appropriate semicircle names because the third letter in there gives the reader direction. Now, we are going to be moving into a last relationship we find within our circle known as this number pi, the ratio of pi. Pi is by definition the ratio of the circle's circumference, c, capital C, of a circle to the length of its diameter. Again, we use that lowercase d. The symbol for pi is the Greek letter pi. So we have this relationship that pi is a ratio of the circumference divided by the diameter. So we're going to be actually using this to help calculate some of the measures within inside of a circle. We actually use this to calculate the measure of the circumference or the diameter or the radius of a circle using this established ratio, this established definition for pi. Now, one question we need to ask ourselves as we move from circle to circle is the value of pi the same for all circles? Is this still going to be, no matter what size diameter, will it always be that this magic number pi is going to be the ratio of the circumference divided by the diameter? And for us, no doubt you said yes, right? It's going to be the same for all circles. It's a postulate for us. We're going to call this the circle similarity postulate. So down below, we've got on our slide here, the value of pi is a constant, i.e. it is the same for all circles. So no matter what size circle we dive into, this definition will hold true for what pi is. And yes, by our assumption that it is, or by our postulate, that it will be then the same value for all circles that we encounter. So when we write pi, you've probably seen this in the past, and I want to make sure that you are doing this correctly. When we write pi, we just simply use the symbol. That will always be appropriate. Just use the symbol within your answer. So you'll see later on as we work some examples using pi that I'll be leaving pi in my answer in some cases. So don't use. I know some teachers will like to use the fraction of 22/7, which gives you that decimal 3.14. Don't do the fraction. Don't use the fraction. Neither use the decimal 3.14. Pi is an irrational number. If we have time, we'll talk about where these beautiful digits come from. But as far as we know right now, just use the symbol whenever you're working with your calculations as far as talking about the circumference of a circle or the diameter circle. We're going to actually just use this symbol within our answer. So this is a good question, or a great question that I've thrown out there, which is where do all those gorgeous digits of pi come from? Well, we may explore this question if we have time, but for now, just know that they exist. There's a project we could do with this, which actually then given your enough resources to you, you can explore this and find where these beautiful digits of pi actually come from. It's actually quite an astounding story as we progress through kind of the evolution of pi, and as throughout time, we see that the as mathematicians slowly and surely got closer and closer to discovering these digits as we expanded the decimal expansion of this irrational number. So it's quite an astounding story that pi has to tell here. But again, if we have time, we'll jump into that. Right now, just know that they exist, that they're there, that there is this number behind the symbol pi that represents this value that we give to this ratio of the circumference divided by the diameter. Now, what we're going to do then is with our definition of pi, we're going to do some slight algebraic manipulation with our definition. So our definition, remember, of pi is the ratio of the circumference divided by the diameter. So what we're going to do is we're going to put the circumference in terms of two different aspects that relate to that circle. The first thing we could do is the obvious. We can put the circumference of the circle in terms of the diameter, meaning that if I want to know the circumference of any given circle, I just simply need to take the length of the diameter and multiply it by pi. That's where we get our first equation here. However, since the diameter and the radius are related, remember that obvious relationship that we found is that the diameter really is twice the radius, we could take that diameter out and replace it with 2r. Thus, we have a second way of representing the circumference of a circle in terms of the radius rather than in terms of the diameter. So the radius, it's going to give us the same length. It's just we will be working with the radius value rather than directly with the diameter value. So we just simply double the radius, attach pi to it, and we've got ourselves a circumference. So what we're going to do is actually these last several slides, we're going to do some examples finding missing measures inside of a circle. Now here's the beautiful part about a circle. All I need to do is give you one measure, and you can tell me the rest. For example, I'm going to give you in this slide here the measure of the radius. With the measure of the radius, you can actually give me the length of the diameter and the length of the circumference. And what we're going to do is we're going to give our solutions in exact form, meaning we'll leave pi in our answer. That's why earlier in the slide I just said, hey, pi will do, the symbol pi will do. We're not going to be using decimals. We're not going to be using that fraction 22/7. We're just going to use our symbol pi. So we're given that the radius of our circle in this example is 16. So the beautiful part again is if I give you one segment or one measure inside of the circle, you can give me all the other measures. So let's start with the radius 16. Well, then the easiest of these two to discover next would be the diameter. Simply to take our radius, double it, and we get then the length of our diameter. So there's our radius of length of 16. So our diameter would then be a length of 32. Now with our diameter, it makes it very easy for us then to use our equation for our circumference in terms of our diameter, and then plug in our diameter to then find out what the value of our circumference is. So from here, all right, I'm going to take my diameter. Actually, I'm going to write out this equation first. The circumference of our circle is really just diameter times pi. So what we're going to do is just going to take our diameter, pop that in there, and we get our circumference value, 32 pi. Now from here, it's going to be tempting for you to touch a calculator where you're going to say, oh, let me actually just multiply 32 times pi. Don't, okay, don't do that. Our answers are going to be left with pi in them. So again, here are the three segments measures that we can actually discover inside the circle. If we're given the radius, we can then find the diameter, and then we can use that to find our circumference. Now let's change our story a little bit in this next example. Instead of me giving you the radius, let me give you the diameter. Now the diameter has a length of 16. We're going to use this to find the length of the radius and the length of the circumference. And once again, we're going to leave our answers in terms of pi, meaning leave pi in the solution. So since our diameter starts off at 16, I need to work backward to figure out what our radius is. Well, our radius is then going to be half of the length of diameter, and that means we have a radius length of 8. Now, either way, I can then use either the diameter or the radius to find my circumference. I'm going to still go with the relationship that the diameter has with my circumference, just simply diameter times pi. So I take my diameter, pop it into my equation. We get 16 pi here, and that would then be our length of the circumference. So again, leave it in exact form. Don't multiply 16 times pi on a calculator. Just leave it as 16 pi, and there we have it. There's our solution of finding the missing measures inside the circle. Let's do one more. Let's now, instead of being given the radius and the diameter, let me give you the length of the circumference, and then you can work backward to find the length of the diameter and the radius. So let's find then the length of diameter and radius if the circumference has a length of 16. So our circumference C is 16. Well, we actually have two relationships for circumference. We have one set up for the diameter relationship and the other for the radius relationship. Either one is fine. It's going to give us the exact same solutions for the diameter and the radius. Now it's gonna get a little wonky here in just a second, but you'll notice that we are just going to leave our answer just as it is. So a circle has circumference of length 16. Well, that circumference equation, I'm going to look for our diameter first, is the diameter times pi. So the 16 is going to come and get plugged into our circumference first here, and we're going to solve for our diameter. So I'll think algebraically, how am I going to do this? I'm going to divide both sides by pi. So when I do that, I get my diameter length is just simply 16 divided by pi. And there is our diameter. Now, that's going to bother some students like, ooh, that's kind of nasty, right? 16 divided by pi. Again, don't touch the calculator. We're going to leave it just in that fraction form, 16 over pi. Now let's move on to our radius, okay? So there's two different ways we can approach this. I can either take my diameter and divide it in half to get my radius, or I can go and use my other relationship that I have for my circumference, which is 2r pi. Just I can plug 16 in again here and then solve for my length of the radius, which in this case I had to divide both sides by 2 pi. And so by doing that, you can see, oh, I'm going to take 16 and divide it by 2, which would have been the exact same answer I would have gotten if I just took 16 piths here in my diameter, divided that in half as well. I get the exact same answer. So 16 divided by 2 is 8, so there's 8 in the numerator, pi gets stuck in my denominator, and there we have it, our missing radius. Again, leave it in exact form. Don't touch the calculator, just leave pi in your answer. You'll be asked to do the exact same thing on your worksheet as well. So we've come to the end of our lesson 9.1, dissecting our circle, looking at the components within inside of it. We explored a lot of definitions. We've seen what a circle is by definition, the segments that go inside of the circle, the radius, the chords, the diameters. We talked about the circumference and how we cut the circumference into the portions of arcs, and then using that relationship of pi, we can actually use this to find missing measures within inside of our circle if we are given one of those measures. So please be sure to hop over and take a look at that 9.1 worksheet. If you do have any questions on that, please don't hesitate to email me with that. Be good and do good.